In this lecture, we're going to continue our discussion of discrete systems. As a reminder, there are 6 steps in all discrete system problems. The first one is to divide the system into elements and label the local and global nodes. Then we apply the governing law at each local element level, which means we apply it to each element individually. Then we construct the local stiffness matrix based on our governing laws and the properties for each individual element. Then we apply the local stiffness matrix into the we assemble the local stiffness matrices into the global stiffness matrices by using continuity of the primary variable and a balance of our secondary variables. Next, we apply our boundary conditions, and lastly, we solve our problem. So previously, we went over how to solve a system of discrete springs. Today, we're going to look at another form of discrete system, which is the axial deformation of bars. So if I was to draw a bar element, I would have, here's my bar, it has a length, it has 2 ends, I have my displacement at end 1, I have my load at end 1, I have my displacement at end 2, and I have my load at end 2. It also has an modulus of elasticity and a cross-sectional area. So if we remember from solid mechanics, we have our strain, which is our change in length over our initial length. We have our stress, which is our modulus elasticity times our strain. We have our load or our force, which is our Q, which is our stress times our cross-sectional area. If we combine all of these equations together, we get that our load is equal to our stress times our cross-sectional area, which is our modulus times our strain times our cross-sectional area, which is our modulus of elasticity times our cross-sectional area divided by our initial length times the relative displacements between the 2 ends of our rod. I can write a similar equation for node 2. And again, if I put these into a matrix form like I did before, I would have our load at our 2 ends is equal to our modulus elasticity times our cross-sectional area divided by our initial length times 1 minus 1 minus 1, 1 times our displacement at our 2 ends. This becomes our matrix KE, where our modulus elasticity times our cross-sectional area divided by our initial length is sort of like our spring constant in the previous work with the springs. So we're going to look at an example. In this example, we have a stepped bar supported by springs on both ends. We want to determine the displacements in the springs, the stresses in each portion of the stepped bar, and we want to neglect the weight of the bars and assume that the bar experiences only axial displacements. So we're going to look at this free body diagram. Looking at the free body diagram, we can see that Q12 plus Q21 has to equal 0. So that is right here, and that is because there is no applied load at that point. This also indicates that we're going to add equation 2 of element 1 to equation 1 of element 2. Now, if we look at global point 3, so if we look at here, we're going to see that we have Q22, so the load at N2 of element 2, plus Q31, which is the load at N1 of element 3, minus P is equal to 0. So that's our balance of our forces. Another way of saying it is that Q22 plus Q31 is equal to P. But also what it's saying is you're going to add equation 2 of element 2 to equation 1 of element 3. The last one we're going to look at is point 4, where we have Q32 plus Q41 is equal to 0. Again, if there's no applied force at that point, the sum of the forces at the two nodes from your elements has to be equal to 0. And this would be adding equation 2 of element 3 to equation 1 of element 4. So what does our system of equations look like? Well, our first equation is equation 1 of element 1, which is K1 U1 minus K1 U2 is equal to Q11. And then if I add equation 2 of element 1 to equation 1 of element 2, I'm going to get minus K2 U2 K1 U1 plus K1 plus K2 U2 minus K3 U3 is equal to Q12 plus Q21, which is equal to 0. Then I have minus K2 U2 plus K2 plus K3 U3 minus, that's 2 K3 U4 equals U2 2 plus U3 1, which is equal to minus P. And then we have minus K3 U3 plus K3 plus K2, K3 plus K4 U4 minus K4 U5 is equal to Q32 plus Q41, which is equal to 0. And last we have minus K4 U4 plus K4 U5 is equal to Q42. Which in matrix form is K1 minus K1 minus K1, K1 plus K2 minus K2 minus K2, K2 plus K3 minus K3 minus K3, K3 plus K4 K4 minus K4, K4 times our displacements U1, U2, U3, U4 is equal to Q11, Q12 plus Q21, Q22 plus Q31, there is a U5, Q32 plus Q1, Q42. So you can also write this in indice notation because it's a lot neater and it's good practice because MATLAB is typically used to solve a lot of these problems. So in indice notations, it's K111, K112, K121, K122 plus K111, so K211, K212, K221, K222 plus K211, K311, K331, K312, K321, K322 plus K411, K412, K421, and K422. Where again, K111, this is your element, and this is your equation number, node number also. It's what's connecting those 2 points. It's what connects point 1 to point 2. It's element 1, and it goes from end 1 to end 2. So we need to figure out our values of K1, K2, K3, K4 for our problem. So K1 is equal to 20, is equal to 2 times 10 to the 6 pounds per inch. And K4 is equal to 10 to the 6 pounds per inch. K2 is equal to our modulus elasticity for element 2 times our area for element 2 divided by our length for element 2, which is pi times 2.5 squared times 10 to the 7 divided by 4 times 8, which is 6.136 times 10 to the 6 pounds per inch. And then K3 is pi 2 squared over 4 times 10 times 30 times 10 to the 6, which equals 9.425 times 10 to the 6. So we have our assembled system of equations. We know all of our values, but we still can't solve the system because we need to apply our boundary conditions. And what are our boundary conditions? Well, our boundary conditions are, well, U1 is equal to 0, U5 is equal to 0. F2, which is equal to Q12 plus Q21, is equal to 0. F3 is equal to minus P, which is minus 200 times 10 to the 3 pounds. And F4 is equal to Q32 plus Q41, which is equal to 0. So what we're going to do is we're going to condense our system of equations down, which means we're going to remove rows and columns that we don't need, based on our known primary variables. So I want to get rid of columns 1 and 5, and since I want to get rid of columns 1 and 5, I'm also going to remove equations 1 and 5. So my condensed equations are K1, 2, 2. Times our unknown displacements, U2, U3, U4 is equal to 0 minus 200 times 10 to the 3, 0. So that is the system of equations that we are trying to solve. You can plug that into MATLAB or your favorite matrix solver, and you will find out that U2 is equal to minus 6.252 times 10 to the minus 2. U3 is equal to minus 8.290 times 10 to the minus 2. U4 is equal to minus 7.495 times 10 to the minus 2. So spring 1 is compressed by 0.06252 inches, and spring 2 is elongated 0.075 inches. So we solved most of the problem. We've gotten our unknown displacements. We know the compression and elongation for our springs. So now we have to find our reaction forces in order for us to find our stresses. To find our unknown reaction forces, we're going to go back and use the rows that we previously eliminated, mainly F1 and F5 are equal to K112, K421 times U2, U3, U4, which I left out columns 1 and 5 again because I would be multiplying by 0. However, nothing stops you from going back and using the full system of equations to solve for your unknown forces, and it's also a good check because it also should spit out the forces that you already know. So this yields that our reaction force at point 1 is 1.2505 times 10 to the 5 pounds, and F5 is 0.7495 times 10 to the 5 pounds. We want stress, so to determine stress we need to find our load Q2 and Q3. So again, we're going to look at our free body diagram and work this through. We know that F1 is the same as Q11, which has to be equal and opposite to Q12 since the load in our bar at our two ends has to be equal and opposite. And Q12 is equal to Q21 since Q12 plus Q21 is equal to 0. And then we have, well, Q21 is equal to the opposite of Q22, which is equal to P plus Q31, since Q22 plus Q31 plus P has to equal 0, which is equal to P minus Q32, since Q31 is the opposite of Q32. So we can solve for Q32. So Q32 is equal to F1 is equal to P minus F1. And we can solve for Q22, which is equal to the opposite of F1. So we get our stress in our aluminum, which is element 1, is Q22 over A2, which is minus 1.2504 times 10 to the 5 over 4.9087. And the Q in our steel, which is element 2, is Q32 over A3, which is 2 minus 1.2504 times 10 to the 5 over 3.1416, which is 23,858. So that's the governing law for elongation in bars. In the next lecture, we will go over torsion of bars.